Just take a look around you for a second. That car that gets you to work, the massive crane building our cities, all of these things operate under absolutely immense stress. So what stops them from just shaking apart? Well, the answer is a kind of magic: invisible engineering. Today, we're going to pull back that curtain and reveal the hidden principles that are literally holding our world together.
No, seriously, think about it. You've got thousands of controlled explosions happening inside the engine every minute, constant vibration from the road, the sudden shock of hitting a pothole. A car is basically an orchestra of controlled violence. So what's the secret? What is the invisible logic that prevents it from rattling itself into a pile of nuts and bolts right there on the highway?
Well, the answer is in this hidden world of machine design. It's like a secret rulebook that engineers use to manage incredible forces and control motion. So we're going to go inside the machine and explore the core principles that make what seems impossible, well, possible. Let's get started. Okay, so where do we even begin? Let's start with the most fundamental challenge of all. How in the world do you convince two separate pieces of metal to act as one single piece? I mean, every complex machine is built from simpler parts, and the joints holding them together, those are the true foundation of its strength.
One of the most elegant solutions we have today is welding. By applying intense heat and sometimes pressure, you're not just sticking materials together, you're actually fusing them at a molecular level. What you're seeing here is a butt weld, where two plates that were once separate have been melted down and reformed into a single continuous piece of metal. It's incredible.
But as always, it's never that simple, right? Engineering is all about trade-offs. Welding gives you unbelievable strength in a lighter joint, but all that intense heat can subtly weaken the metal right around the weld. Now, bolting avoids that heat damage, but it adds weight, it adds complexity, and it adds cost. It's this constant balancing act between strength, weight, and the integrity of the material itself.
And hey, before modern welding, riveting was king. I mean, just picture the Eiffel Tower, or those classic old steamships. It's such a simple, powerful idea. You insert a hot metal pin through two plates, and then hammer a second head into place, locking them together as it cools and shrinks. And how those plates are arranged is key. You can overlap them in what's called a lap joint, or place them edge to edge with a strap, creating a butt joint. It's an ancient technology, but it's incredibly reliable.
Okay, so our machine is held together. Awesome. But now we've got the next challenge: power. How do you connect a violently spinning engine to wheels that are standing still without a massive, destructive jolt? How do you smoothly control all that raw power on demand? Well, this brings us to the absolute genius of the clutch.
This right here is the clutch, and it's a masterpiece of controlled friction. On one side, you've got the driving shaft, spinning with all the engine's power. On the other, the driven shaft, which is connected to the wheels. The magic happens right in the middle. Think of it like this. It's like bringing your hands together to clap. When the pressure plate squeezes the clutch plate against the spinning flywheel, friction grabs hold, and that transfers the engine's rotation to the wheels. Then you press the clutch pedal, they separate, and poof, the power is instantly cut.
But of course, one size doesn't fit all. A car has plenty of space for a big single-plate clutch that can just air-cool itself. A motorcycle, on the other hand, is all about being compact. So what's the solution? A multi-plate clutch. By stacking several smaller plates together, engineers can handle immense amounts of torque in a tiny, tiny space. The catch? All that friction in one small spot generates so much heat that it has to run wet. I mean, it's literally bathed in cooling oil to keep from melting. So we can join parts together, and we can make them go. But you could argue that the most critical function of any machine is its ability to stop. And this is where we flip the script and use friction not to create motion, but to control and completely destroy it.
So what is a brake, really? At its core, it's an energy converter. Think about it. A speeding car has a colossal amount of kinetic energy. That's the energy of motion. A brake's only job is to take all of that energy and, through intense friction, transform it into a totally different kind of energy: heat. The energy doesn't just disappear. It's just safely radiated away into the air, bringing the car to a nice controlled halt. Now, this is where design gets really, really clever. Normal brakes need a lot of force to work. You push the pedal hard, the brake pushes on the wheel hard. But what if the brake could help you out? What if the very motion that you're trying to stop could be harnessed to apply the brake even more forcefully?
This is the genius of the self-energizing brake. Just look at the geometry here. As the drum spins, the friction from the brake shoe doesn't just slow it down, it actively pulls the shoe inward, wedging it even tighter against the drum. The brake literally uses its own motion to brake harder. This clever design multiplies the driver's effort, making the entire system way more powerful and efficient.
All right, for our final piece of the puzzle, let's talk about pure, effortless motion. We've got parts that need to spin, wheels, shafts, turbines, at incredible speeds. How do you let that happen for years and years without friction just grinding everything to a halt? Well, the answer is one of engineering's greatest unsung heroes.
Meet the rolling contact bearing. You know, it's so good at its job, it's often called an anti-friction bearing, which is pretty amazing. The design is so simple but so profound. You have an inner race that's connected to the spinning shaft, an outer race connected to the stationary housing, and then sandwiched right between them are the rolling elements. In this case, they're balls, all held neatly in place by a cage. But the shape of that rolling element is absolutely critical. A ball bearing, like on the left, touches the races at just a tiny point. This means you get incredibly low friction, which is perfect for high speeds, but it can't handle very heavy loads. A roller bearing, on the other hand, makes contact along a line. This spreads the load out, allowing it to support immense weight, but with just slightly more friction. It's another one of those classic engineering trade-offs. Do you want speed or do you want strength? So we've taken a journey right through the core of machine design, from the static strength of a simple weld to the dynamic grace of a bearing. But these aren't just isolated components. They're a whole system of principles working together. When you boil it all down, you get these four pillars. You've got joining, to build a strong foundation. You've got controlling, using devices like the clutch to manage power. You have stopping, using brakes to safely absorb motion. And finally, enabling, which lets things move smoothly with near frictionless bearings. These four functions are working in perfect harmony inside every sophisticated machine that we rely on every single day.
Now, these principles were really perfected during the industrial age. But today, we're entering a whole new era of smart materials, AI-driven design, and nanotechnology. So you really have to wonder, what new, invisible engineering will hold our future together? And what will the next generation of genius design even look like?